subsequent study sessions will also cover concrete, wood, and masonry. But today, we'll focus on steel. So steel is, obviously you see it everywhere in structural framing and a lot of the structural construction. So steel, the composition of it is mostly iron plus carbon plus other chemical elements. And different composition produces different type of steel, which I will go through in a second. So a concept to remember is that the amount of carbon determines the malleability and strength of steel. So if there's too much carbon, it makes the steel harder and more brittle. And if there's too little carbon content, it makes the steel more malleable and weaker. So a quick question here for you to make a guess. Which type of steel below has more carbon? A, cast iron, B, wrought iron. You can just make a guess. Okay, let's go to the answer is A, cast iron, and I will explain. Okay, so that brings us to the introduction of different types of steel. So the type of steel is dependent on the chemical composition and as well as the way it's manufactured or produced. So cast iron, which we just saw in the question just now, it has a lot of carbon, so the answer is cast iron. So that's why it's strong and brittle. Wrought iron, on the other hand, it contains less carbon, and that's why it's weaker and malleable. So I only include the most key points here for each type of steel for you to memorize. But this is definitely not the full description of each type. But just highlighting the most important points that I feel like you should be aware of in order to take the exam. And then we also have hot rolled steel and cold rolled steel. So the difference between these two types is the way it's produced. So hot rolled steel, it's milder steel compared to cold rolled, and it's commonly used for wide flange beams, angles, rebars, etc. These type of structural members. And then for cold rolled steel, it's also called cold formed steel or cold drawn steel. It's stronger than hot rolled steel. And one advantage of cold rolled steel is that it's very lightweight. So it's commonly used for extra thin cabling. It's very strong but thin and lightweight. And so also commonly used for cross bracing, framing such as metal studs. So what you usually see inside a stud wall, the metal channels used is usually the cold rolled steel, or the channels in suspended ceiling system. And then we also got weathering steel, aka cotton steel. So if you see this term cotton shows up on your exam, you would know it's referring to a weathering steel. And it means this type of steel forms a stable rust-like appearance after several years of exposure to weather. You may have seen it in real life. Let me show you a picture quickly. Weathering steel. It's this rust-like, this type of steel eliminates the need for painting. So it forms this layer of rust over years of exposure in the weather. So, okay, let's go back to, just so you know what weathering steel looks like. And then we also got tempered steel. So tempered steel, it got reduced hardness. So the way it's manufactured makes it less hard, but with improved elasticity strength and ductility. So more types of steel. We got white cast iron. This type of steel contains low silicone content and it's rarely used in construction. And then we have gray cast iron. It's opposite of white cast iron. It has high silicone content and commonly used for coating, such as the hardware or plumbing valve coating, etc. And then stainless steel. We hear it all the time. It's very corrosion resistant. It contains iron and carbon, nickel, chromium, very weather resistant. And then also two more types of steel that's very corrosion resistant is zinc plated steel and hot dipped galvanized steel. So these two types of steel here is very similar in the way that they're both coated with zinc. But the only difference is the thickness of the zinc coating. So the zinc plated steel, it has a thinner layer of zinc coating. And the zinc coating provides protection against weather or corrosion. So the zinc coating makes this type of steel very weather resistant as well. And then hot dip galvanized steel got a thicker layer of zinc coating for stronger protection. So it's even more corrosion resistant compared to zinc plated steel. And then, so that's like an overview of some of the most commonly seen types of steel. And then we got structural application of steel. Okay, so here we have a comparison of I-beam and wide flange beams. So wide flange beams are usually abbreviated as WF beams. It got wider flange. So these two parts at the top and bottom is the flange of the beam, and then the middle portion is the web. So the wide flange beam compared to traditional I-beams is that they have wider flange and a thicker web, making these wide flange beams more structurally efficient than the I-beams. So it's I-beams have been largely replaced by wide flange beams these days for their structural efficiency. And then, oh, sorry, let's come back for this for a moment. So usually, a wide flange beam is represented by this designation. So W means wide flange. And then this first number here is the nominal depth in inches. The second dimension is for the weight, pounds per linear foot. So my next question would be, so yeah, if you see a beam that says W12 by 120, it means that this beam is 12 inches deep. Also represented by this D here for the depth. And then here I listed out what each of this number means. Yes. So, okay, so that's showing you how to read the numbers. And then below are wide flanges of two proportions. Which one is used for beam and which for column? Make a guess.
Left spring.
Yes, that's correct. So yeah, so these are both very commonly produced proportions for the wide flange beams or wide flange columns. And then the column got even wider flange and a thicker web for better structural support of the vertical loading. And then some other commonly seen steel members in construction. We got wide flange, which we just talked about, the I-beams. And then this is a structural T. Structural T is like cutting the wide flange beam in half at the web. And then we have a C channel. Over here, we got angles, unequal legs or with equal legs. And then tubes, round tube or square tubes are both very commonly seen and used. And then steel application in long span structures. So in cases where a standardized beam cannot achieve the span, you could look for other types of steel structures to achieve the span. First, we have castellated steel. This type of steel is like the way it's produced is literally illustrated here with these diagrams. It cut this way, splitting the standard wide flange beam and then stacking it to create a beam a castellated beam that's deeper at the depth, but with lighter weight. So for the same depth of beam, it got lighter weight because of the openings that it created. So the castellated steel is usually used for long span structures. And then these openings could be used for ductworks, conduits, pipes, etc. So it's also very spatial efficient. And then we got plate girder, which is another very structurally efficient type of horizontal member used for long span. The girder is built up of steel plates. So the steel plate in the middle acting as the web, and steel bars or angles to form the flanges, just like what it's illustrated here. And then more types of steel structure to achieve long span would be steel arch, which is very, very efficient, carries a much greater load than a horizontal beam can support, and it can span large spaces. And steel cable, especially high strength steel cables, are very...
Hi, excuse me, sorry I'm late.
Hi.
I am Alfred.
Oh, you're Alfred.
Yeah.
Claire mentioned you
Oh,
to me.
hi, hi.
So okay, I need to, maybe I should
Sorry.
pause.
I just get off work.
Maybe I should pause because, or maybe I should keep going, sorry.
I don't mind, just keep going.
So feel free to contribute.
Okay.
Yeah, because he also just recently licensed.
Oh,
Yeah.
Great. Last 3 days ago, my last
Really?
week,
Oh,
yeah.
only 3 days ago.
Yeah, it's
So you're
within this week, so I'm still fresh.
Oh my
My
God,
mind is still fresh.
perfect. Perfect.
Yeah.
So feel free to contribute
Yeah,
to my.
sure. I mean, I don't mind if I still remember the content. Well,
I bet you do. Yeah, so today we're just gonna focus on steel, like the steel properties and its application in construction. So right now I'm just covering some of the most important, like commonly used steel structure in long span construction. And then on this slide, we got steel arch, which is very capable of spanning large spaces. Steel cable, also very efficient for long span construction, and they resist loads by axial tension. And then we also got steel truss. So truss, very commonly seen structure. It's composed of straight members that form a number of triangles stressed in compression or tension. So compression or tension is very stable type of loading support. So when you're being stressed in compression or tension, you're more capable of supporting the loading. So that's why truss is very efficient for long span structures because of their primary reliance on compression or tension to resist forces, and also due to its lightweight composition, which makes the high strength to weight ratios. So here I copied in some commonly seen types of trusses, and then you could determine whether a diagonal member is in compression or tension by imagining there's a point load acting downward on the center of the truss and making downward bending of the truss. So if you imagine this truss is being bent downward, making a smiley face, then you could find out whether each of the diagonal member is being compressed or in tension. So for example, in this how configuration, the diagonal member will be in compression. And then when the direction is on the other way for the diagonal members, in the Pratt configuration, the members will be in tension when it forms a smiley face, if that makes sense. Yeah. So, and then we have open web steel joist. So these horizontal members are open web steel joist, and they are being supported by joist girders. So the middle members are steel joist, and then this main horizontal support connecting to the columns and supporting the joist is the joist girders. So let's look at my description here. Right, for open web steel joist, it's standardized into 3 major groups. There's K series, LH series, and DLH series. The K series it achieves the shortest span, less than 60 foot. And then LH series, it can achieve a longer span, but less than 96 foot. And then for DLH series, you can achieve the longest span up to 144 foot. So it's important to know what each of the series means on the exam. Mostly know the difference in its span distance. And then, right, for joist girders, it's designed to serve as primary structural members to support the evenly spaced open web joist. So just getting to know what each of these terms mean in the structures. And then next we got cambering is very important concept to know, just so you don't freak out when you see cambered on your exam. So cambering literally means pre-curving a beam so that it can resist greater weight, and then lessening the impact of heavy loads on the structure. So usually, this is literally what it would do if you're cambering a beam. It's like pre-curving it. And then in the diagram below, when the curved beam is used to support the roof, it's pre-curved with the calculation of the bending incorporated. And then it's expected to be flattened out when it's fully loaded. So this way, it's more structurally efficient. And then here I have a summary of long span structures. Most economical would be steel cables. So steel cable is most cost effective among other types of commonly used steel structures. And then steel arches can achieve the longest span, usually between 300 and 350 foot. Steel heavy truss can achieve up to 300 foot of span. Concrete thin shell dome is below 250. Glulam arches would be 100 to 250 foot. Open web steel joists would be up to 150. Intermediate span rigid frame, which I have a little diagram explaining what it is. So rigid frame has a sloped roof with a rigid moment resisting connection. So each of the joints is fixed connection. This whole frame is rigidly connected. Or sometimes it's just one continuous member. So rigid frame is also very structurally efficient and can resist lateral loads or rotational moments. And then plate girder, which we just talked about, can achieve usually up to 70 foot. Precast concrete planks up to 50 foot. Wood eye joist 20 to 45 foot. Dimensional number spans the least distance, and it's below 20 foot. And then just so you get an idea of the capability of each type of long span structures. Steel connections. Okay, we're gonna talk about steel connections now. Which type of connection is shown in the diagram on the right? Shear connection or moment connection? Make a guess. So the answer is
Hey.
I'm gonna explain why. So let's talk about what is moment connection and what is shear connection. So moment connection, both the flange and the web of the beam is connected to the column. Meaning it's structurally engaged to the column. And therefore, so I have a little diagram for you to look at. The moment connection, you can see that the flange is being connected either through welding or bolted connection, and both the web and the flange is being physically connected to the column. That defines what a moment connection is. So this way it can resist, because the flange and the web are both engaged to the column, it makes it resistant to lateral loads. Because I'm gonna talk about more details in a second, but just memorize the difference for now. How to identify which one is shear and which one is moment connection. So that is the biggest difference between the two connections, whether both of the flange and the web are being connected to the column. So you can see here in the shear connection diagram, either only the web is connected to the column or only the flange is connected to the column. So that's why the shear connection is less resistant to lateral forces or rotation. And a moment connection, because everything is connected to the column, it's equivalent to a fixed connection in my understanding. And it's more costly and time consuming in construction. For a shear connection, it's equivalent to a pinned connection. I'm gonna explain what fixed connection and pinned connection means in a second. And for a shear connection, it's compared to moment connection, it's less costly and less time consuming for connection, for construction, sorry. So right here, we are gonna cover 3 types of major connections in structural construction. First, we have roller connection, which you can see in the diagram here. It's being supported by a roller. So in this type of connection, it can resist external actions of vertical translation only. So if you move it vertically, it can resist that action. But if you move it horizontally, or if you rotate it, it cannot resist that type of loading. So that's why in the reaction, so the vertical translation, horizontal translation, these type of actions are external actions, but then internally within the structural members, it will provide support reactions. So in the roller type of connection, the roller provides an upward support reaction because it can only resist vertical loading. So it can only resist the gravity forces, which is why there's only an upward arrow to show its reaction to the vertical forces. And then in the pinned connection, it can resist vertical and horizontal forces, but not rotational moment. So in the pin connection, it's like you pinned something down and then you can still rotate it. That's why it cannot resist rotation. But if you try to move it vertically or horizontally, it can resist that. That's why in the support reaction diagram, you could see arrows pointing upward to resist the downward vertical loading, and then pointing this way to resist the opposite horizontal loading or forces. So the support reaction is always in the opposite direction of the external actions to resist the external loading. And then in the fixed connection, it can resist all types of forces, basically in any direction. You can resist vertical and horizontal translation, and it can resist rotational moments. So basically it's fully fixed and you cannot move it in any way, in simple words. So which is why in the fixed connection reaction diagram, you'll see arrows resisting vertical loading and arrows resisting horizontal loading, and also a moment arrow resisting rotation. So, okay, so external actions, it's been defined here as externally applied loads onto the structural member. So we commonly see tension pulling the member away, or you are compressing the member, making it being in compression. And then this is torsional forces. And then we also have shear forces acting in opposite directions. So here in the bending diagram, you can see okay, imagine this is a beam. When a beam is being bent upward like this, the top part of the bending is in tension. And then the bottom part of the beam is in compression. So this is very important concept to know. Always remember if it's being bent upward, the top part is in tension and the bottom part is in compression. If it's being bent downward, making a smiley face, then it will be the opposite. The bottom part would be in tension and then the top part would be in compression. And then there's also shear happening along the imaginary line internally within the member, because it's acting in opposite directions. So that explains what shear forces are. And then moment forces is the forces produced by bending. And the rotation axis is perpendicular to the plane. So that's the difference from torsion. In torsion, the rotation axis is aligned with the member's axis. So next, we have more diagrams here. So normal force, okay, normal force means compression or tension or axial forces. So the force F2, it's acting along the axis of the member itself. So in this way, the F2 would be making the member in tension here. So, and then the shear force, if you got a member that's cantilevered out like this and supported on one end with the F1 force being applied on the other end, you get the shear force acting on it, represented by the green arrows here. And then in the bending moment, in the same scenario where you have the structural member cantilevered out and being supported on one end with moment, M represents moment, rotation, with a force, rotational force that's trying to upturn this member, that it creates the bending moment. Okay, so next. Which diagram? This is very important question to memorize. Which diagram represents the most plausible support reaction in the foundation against the forces applied to the building? Select the two best answers. So in this scenario, this bold black line represents the building profile with footing foundation. And then the arrows representing the external forces acting onto the building. So the question is asking, what's the support reaction of the foundation? So I just mentioned support reaction is always in the opposite direction of the external action. So you could try to guess if the direction of the external forces are being applied this way, what would the support reactions be in the foundation? Always opposite to external loads. You got one right.
I think F is right.
Yeah, if you combine both of your answers, you got full marks. E and F. Yay. Okay, I'm gonna explain why. So in this scenario, you see there's downward loading, which is usually the gravity of this whole building, the weight of the gravitational loading of the building itself. And then there's lateral loading. You can imagine it being wind load or whatever, lateral loads. So there's two scenarios, very plausible scenarios in this case. That's why there's two best answers. If it's, I'm gonna explain F first. If it's in the F scenario, you could see that the foundation, so obviously to resist to resist the vertical loading, you must have an upward reaction, which is what this footing is doing. It's trying to support the gravity with an upward action. And then for the other footing, there is a downward arrow. And this is because in this scenario, the wind load is assumed to be stronger than the gravitational loads. And that's therefore, when your wind is very strong and your building is lightweight, it tries to like pull, like overturn the building in a way. So it tries to push the building to the right? If you have very, very strong wind and your building can barely resist it, then your building tends to fall to the right. And when it tries to fall to the right, it creates an pulling up action onto the footing on the left. And therefore, the footing will have a reaction opposite to that pulling moment. And therefore, there will be a downward support reaction to fight against that overturning force. If that makes sense. Yeah, so in this case, why there is a downward arrow for this footing is because we're assuming the wind load is very strong compared to the gravitational loads. Therefore, this footing has to pull the building down and pin the building down to prevent it from being overturned by the wind load. And obviously, there's also reaction pointing the opposite direction of the wind load. And then in the E scenario, we are assuming the building itself is already super heavy and it's greater than the wind load. Therefore, there's not much overturning due to the wind load, and both of the footings are just providing upward support for the building. So there's only both of the vertical arrows are pointing up in the footing. And then, so the horizontal arrows are very self-explanatory. It's fighting against the wind load in the opposite direction. And then this rotational moment arrow, it's fighting against the clockwise rotation that the wind load is trying to produce. So therefore, there is a counterclockwise reaction to that.
Does the wind load always be in clockwise direction?
Yeah, because the wind load is being applied on the left side of the building. Yeah, therefore, in this case, it creates a clockwise moment. Yeah.
The wind come from the right
Yeah,
side, and the whole
if the
thing will
wind,
be
right.
reversed.
If the wind is coming from this direction and hitting from the right, then it creates counterclockwise moment, and
The whole thing
then
will be
yeah, and then your foundation will be providing clockwise reaction to it. Yeah, just always remember it's opposite to the direction of the external action. So, but this is very important question. I got this question on my exam. Not or similar, not exactly the same.
Okay.
Very similar question. It shows up all the time.
How did the exam ask? Is exactly
Very
the same?
similar.
Oh,
Yeah.
similar.
You also need to look at these diagrams for the support reaction arrows and pick the
In
best
PPD,
one.
right?
In PPD. Or maybe PDD too. I don't remember. I think most likely PPD. Yeah. But yeah, it's important to understand external action versus support reaction of the structural members. And then next. Okay, more on steel connections. Dog bone cuts. Honestly, I don't know what exactly it means, but I typed out what I read from my study material. It's for seismic control. I think that's all you need to know probably. Whenever you see dog bone cuts, you know it's for seismic control. So it acts like a control valve for seismic forces, deforming so that there is not a catastrophic failure of the welded or bolted joint. I can't elaborate on what it means. That's all I know. Just so you are familiar with this term, is for seismic control. And you don't panic if you see it for the first time on your exam. And then backup bars. Backup bars. That's what this little bar is illustrating. So backup bars is for preventing the welding arc from burning through the flange. I will explain more later for this term. Stiffener plates. So stiffener plates, these two, it's welded onto short of the web at the point where extra forces are going to be applied. So it's basically reinforcing the flanges. That's what a stiffener would do. Splice. Splice is a member for joining two smaller members to become one continuous member. So in this diagram here, it shows a column splice. So when you need to connect two smaller columns to make one continuous deeper column, you will use a splice plate and bolt it onto the column flange. And then more on steel connections. Okay, so I summarized 3 types of connection, like physically connecting steel members in structural construction. The first being riveted connection. If I'm understanding this correctly, a riveted connection would be, so you have this a mushroom shaped like thing that's called a rivet. And when you're making the connection, you would heat it up so that it becomes molten, and then when it's molten, you clamp it. So you press it together to make a clamp, and clamping these steel plates together. That's how I understand how it works. I don't know if I am correct, but that's what I learned when I was studying. But I don't think it's very common these days. But then the second type of connection would be welding. So here I included different types of commonly seen welding. We got the fillet weld. Looks like this. Double fillet, V-groove. It's like welding in the V-shaped gap of 2 separated plates. And then the poodle weld. Looks like the poodle. And then we have single bevel groove weld with backup bars, double bevel groove weld, or partial penetration single bevel groove weld. And then last but not least, we have V-groove weld with backup bar. So what a backup bar does is that when you're welding, so the weld is the blue parts. When you're welding, you're preventing the steel from, how do I say it? Like preventing burning through the steel. So you have a backup bar to act as a back to hold the weld. or it doesn't have to be a bar. You could literally just weld the back first, and then you come back to weld the V groove. So it's just some type of backing for the welding. And then the last type of steel connection will be the bolted connection. And here I highlighted two types of high strength bolted connection. The first being slip critical bolt connection. So in this type of connection, the bolt, this is the bolt. As you can see, it's connecting two steel plates together, and it's operating in tension because it's super clamped to the plate, super tightened to create high friction to resist shearing. And then in the bearing shear bolt connection, it's just snug fit. So this type of slip critical bolt connection, it's the most tightened way of connecting with the bolt. And then this is the snug fit connection. So the bolt is not in as much tension as in the slip critical connection. But yeah, just remember what these two types of connection mean. So but in the bearing shear bolt connection, it's snug fit and just enough to resist shear forces of the two steel plates.
I still don't see the difference.
Yeah, so this one you can see it's just hyper tightened.
Okay.
Yeah, this one is snug fit, so just enough
Just okay.
to clamp the plates together. But then this one, it's more than just enough. It's highly tightened.
Okay.
So that's why the bolt will be in tension. Yeah. So but in this case, the bolt might not be in so much tension because it's only fitting to the plates. Yeah. So
What's the benefit of?
So in the highly tightened connection, it can resist high friction.
Then why everything just
It can resist greater shearing forces. Yeah. So in this one, it's just more loosened, basically. One is more tightened, one is more loosened.
I always question like why we want to do that. Like in what situation you want to just
make it
right enough and
tightened?
not everything just highly tightened.
In case of when there's a lot of shearing, potentially a lot of shearing forces.
Oh, okay.
Maybe
Of the
inside
two
area.
plates.
Yeah,
Maybe that you will need very slip critical. That's why it's called slip critical. Yeah. In cases when the two plates are highly likely to slip and creating the shear forces in opposite directions, then you need highly, If you highly tighten the bolt, then it will less likely. It's just a stronger connection in my understanding. And then more on steel connections. Okay, this is for steel columns. It shows you how a steel column gets connected to the ground and distribute the loading to the ground. So what you need would be usually two cases, mostly thin cases. We have, this is the wide flange column. And then we have okay, let's start from the bottom. We have the grout first. The grout being on top of the concrete ground as the base. Usually it's non-shrink grout. Non-shrink grout means the volume of the grout doesn't shrink after it's hardened. So we have non-shrink grout at the bottom. And then on top of that, we have a leveling plate. The leveling plate is used to make sure the column is sitting on a leveled surface. So we have a leveling plate to ensure the leveling of the surface. And then on top of the leveling plate, we have a column base plate, which is what this would be acting as, the base plate. And then finally, we have the column sitting on top of the base plate and being bolted down with the anchor bolt. So just what these bolts are doing, connecting the column onto the base plate. And then in this case, it's slightly different in that instead of having a leveling plate, you will have leveling nuts to level the base plate. So you don't have an additional plate for leveling. You only have a base plate on top of the ground. But then to level the base plate, you use the leveling nuts to make sure it's a leveled surface at the base plate. Yeah. And then girts. Just so you know what a girt is, it's the metal channel that spans between steel columns. And they transmit lateral loads from the exterior walls to the columns. And then they also serve to receive the cladding and hold it in place in the construction. And then here on the right, I just have different types of commonly used girts. So you see this horizontal member here is the girt being connected to the column, and then the cladding would go at the girt to hold it in place. And then so structural slab and steel framing connection. I just summarized two types of commonly used connection when you're connecting a slab onto the framing. So first we have corrugated metal deck or metal pan. And that's what you see here, the corrugated deck, the metal deck. And it's the permanent concrete formwork. So on top of the deck, you have the concrete hardened onto it. So the deck itself is the formwork for the concrete. And you have the deck, and then you pour concrete mixture, and then you don't take the deck out. That's why it's permanent formwork. Because usually if it's temporary formwork, once the concrete hardens, you will remove the formwork. But in this case, the metal deck is the permanent formwork that you don't remove. You just keep it in place with the concrete slab sitting on top. And then the metal deck gets connected to the steel framing, the beams and the columns. And then the second type would be when the slab is self-supporting and there's no metal decking. So in this case, after the concrete slab is hardened, it's self-supporting and you don't have a metal decking below it to support it. And in this case, you would use a shear stud to connect the concrete slab to the beams. So just so you know what a shear stud is, it's used for connecting the concrete slab to. And then I also have a little note here that says the concrete slab acts like a shear wall in the XY direction. And I'm going to talk about shear wall next. So in order to understand shear wall, let's look at moment frame and shear frame. So a moment frame is this one right here, the one on the left. It's a moment resisting frame. What is a moment resisting frame? It means that all the connection at the joints, all the connection between all the structural members are fixed connections or rigid connections. So fixed connection is what we defined before. It resists all lateral or rotational moments, loading in all directions, vertical or horizontal. So that's a very rigid structure for a moment frame. And then it's super efficient to resist lateral loads and rotational moments. So it's very good for resisting wing loads or any lateral loads or overturning moments. And then the shear frame is a frame of pinned connection. So like I mentioned, a pinned connection, it doesn't resist rotation or lateral forces. So how do we increase its capability to resist lateral forces? Is that we would add bracing or shear walls, so that in a shear frame with only shear connections, it can still resist lateral loads or rotational moments. So a shear frame is usually composed with a frame with shear connection plus either bracing or shear walls to help resist the lateral loads. And then here I just have diagrams of different types of bracing. So A is the moment resistant frame, is the moment frame. And then for bracing in a shear frame, we commonly use knee bracing, looks like this, or portal frame bracing at the top of the portal, looks like a portal. And then we have X bracing, very commonly seen, or chevron bracing. What this is also called K bracing because it looks like a K. And then shear walls, which we just talked about, is a shear frame with a wall, a solid wall, to resist the lateral loads. And then for frame tube and truss tube, I elaborated a little more on the right with description. A frame tube diagram like this, it creates a large hollow tube cantilever from the ground. So this whole thing is like a hollow tube, and it's built of closely spaced exterior columns and beams that are rigidly connected to form a very efficient stiff structure. And then for truss tube, so this whole frame tube is like a moment frame, a tube of moment frame. And then a truss tube is very similar to a frame tube. It uses a combination of rigid frame, which is moment frame, and diagonal braces to strengthen its ability to resist lateral loads. And then, so a shear wall could be placed in any plane and act like a shear wall. So it could be the XY plane, the YZ plane or XZ plane. And if you have an enclosed shear wall structure, it can create very strong and lateral load resistant framing. So if the shear wall, the enclosed shear wall is on the core, it forms a rigid core for the building. And if the building exterior skin itself forms the enclosed shear wall, it becomes a rigid perimeter. So this type of shear wall is more stiff and rigid than the rigid core because the shear wall surfaces are larger. So next, we're going to talk about fireproofing structural steel. So fireproofing steel columns. These are commonly seen types. We first have plaster. You enclose this structural steel with plaster. Plaster is fireproofed. Or you could have water plus antifreeze inside it to fireproof it. So the antifreeze will prevent the water from freezing in very cold temperatures and remain as liquid to fireproof. Or you could enclose it with concrete. Concrete is also a good fireproofing material. Or you can apply resistance material. Looks like this. Or you could use sheet metal and with insulating film inside of it. And then last but not least, we have gypsum board. So these are some very commonly seen ways of fireproofing a structural steel. Or we could use intumescent paint. So intumescent paint, this type of paint creates a protective layer for the steel. When it's exposed to high temperatures, it kind of swells up like this and provides the protection against fire. Or we could, so here we have Lally column. So Lally columns is a structural steel with column infill. And then to provide the fireproofing, you have fireproofing insulation on the outside. Just like that. So this infill is the fireproof insulation. And then enclosing the Lally column, which is structural steel with concrete infill. So I think that's it. Okay. What steel structural members are not required to be fireproofed? Do you have an idea? So I read this off of Amber book. It says that the members that only resist lateral forces, and that is their only job, like bracing, are not required to be fireproof. Just keep that in mind, I guess. So you know, not everything, not all structural members have to be fireproof in construction. But most of them do. Okay, what is wrong with, this is another topic. What is wrong with aluminum nail through copper flashing on a roof detail? So what is wrong when you nail down a copper flashing with aluminum nail? Yay! You got it correct. So galvanic action or corrosion is likely to happen. So I screenshotted this from Architectural Graphic Standards. It says here, the metals listed here. So this is an important list with the galvanic number for the metals. So the metal listed are arranged in the order from least noble to most noble. So least noble means if a metal is least noble, it means it's most reactive to corrosion, most likely to corrode. If it's very noble, it's less likely to corrode. So aluminum, being number 1 in the list, it's very likely to corrode when there is galvanic action. And so when you have a very noble metal being in contact with a least noble metal, meaning when the two metals are far apart in this list, galvanic action is very likely to happen.
So what happened 1 and 2?
1 and 2, I guess. Yeah, if aluminum in direct contact with zinc, I guess
fine.
It's fine.
fine,
Yeah,
yeah.
if they are close in the list.
They're closer in the.
Right. Yeah.
the
So
further apart the galvanic actions.
Okay.
right.
It's not
So
about 1 and 8 or something. It's just
yeah.
the difference.
Yeah.
I
Yeah.
saw
Yeah.
The
one
rank.
question in my exam, they put aluminum as
Oh,
as a
really?
third option.
Okay.
So I
Oh.
got 3, I mean, I can't disclose the question, but I got 3 choices. One is, I think that the question itself is aluminum, something like that. But then I got zinc and stainless steel passive,
Mhm.
and
Oh.
another one is like oxidized, whatever. But
Oh. But then zinc would be
just
fine with
pick the one that
aluminum.
is furthest.
Yeah.
Oh,
The
so-
farther apart.
Do you need to memorize the?
No, just remember.
I think you do need to memorize like
You know that
aluminum,
zinc,
zinc,
aluminum
copper.
are pretty dangerous if you put with copper.
Yeah.
But stainless steel is a bit tricky because there are 2 stainless steel.
Yeah,
So
there's
just-
active or passive.
Okay.
Usually you don't have to. I thought it won't be there, but then I got a question on passive stainless steel.
Oh,
And-
yeah.
Yeah, there is an option to pick on steel
No.
and
Oh.
or passive stainless steel. So
Oh,
sometimes they trick you like that.
I
Oh, I
see.
see.
So it's best to kind of
memorize it.
memorize the list. You don't have to know the exact numbering, but
Mhm.
like tin or lead is
Those in between, the middle.
yeah,
one,
it's
those
not
are your-
yeah, it's less likely to show up, but then the extremes ones,
I see.
those ones you just remember if it's noble or like if it's anode or the cathode side.
I see.
Yeah, remember anode means it's least noble, it's very active to corrosion, and then cathode is the good side.
Mhm.
It's noble and least reactive to corrosion. So when two metals that are far apart in the list, they are in direct contact, the least noble one will most likely to deteriorate. Yeah. So summary of metal corrosion is oxidization, meaning a metal just gets exposed to air or moisture or salt, and like what you commonly see in rust. Rust is a type of corrosion. So the solution with that would be you coat the steel with epoxy or zinc. Like I said, the hot dipped galvanized steel or zinc plated steel, those type of steel, because of the zinc coating, it provides a layer of protection against oxidization. So it's less likely to rust if you have a coating of zinc, or you can coat it with polymer. And galvanize it, like I said, stainless steel also very corrosion resistant. And then besides oxidization, we have what we just talked about, the galvanic corrosion, also called galvanic action or electrolysis. This is for the case when 2 metals that are far apart in the galvanic number are in direct contact in an environment of moisture and air. So the solution would be to use an insulator to separate the 2 metals. Just don't make them be in contact with each other. And specifically, it could be a plastic or rubber washer, as long as they are not in contact. So in this case, let's go back to this question. If you nail down the copper flashing with aluminum, and because aluminum is least noble, very reactive to corrosion, and being in contact with copper is very noble, so they are far apart in the list. So you cannot use aluminum nail for copper flashing because galvanic action will very easily to happen. And then aluminum being the least noble metal will likely to deteriorate. So you would never want a nail to deteriorate. Otherwise the flashing will not be nailed down to the roof. So which of the following metals are most resistant to oxidization? You can make a guess. Most resistant to oxidization. less likely to rust.
Gold.
Yeah. Gold and silver. So of the listed metals, gold and silver are the most noble. They're very, very noble. And they're least likely to oxidize or rust. So the noble metals are always the less likely, the more corrosion resistant. Yeah. Either the corrosion being galvanic action or oxidation. What do I have? Oh, this is all I have for today. Okay. So I think in the subsequent section I will cover concrete or wood or masonry.
Sure.
Yeah. But for now, wait, let me pause.